Hello, and what we're going to try to do today, or what I'm going to try to do today, is explain plate boundaries for the whole idea of plate tectonics. This whole idea was formed probably in the 20th century for the most part, with Alfred Wagner back in the 1920s, International Geophysical Year, the late 1950s, all the post World War II submarine hunting information, data, which actually took pictures of the ocean floor. And what we discovered was the largest mountain range on the planet, the Mid-Ocean Ridge, which you can see a small part of it right here. So we're seeing a very small part of a 46,000 mile long mountain range, which has a rift valley running through it. Rift actually means to be ripped apart. This is an ocean floor diagram. You can see the ocean sitting on top. This is an oceanic plate moving to the right. This is an oceanic plate moving to the left. We can see this sort of diagram right here, which is going to represent an earthquake. We can sort of see this release of steam, which is supposed to be the volcanic eruption. Remember, this is not a volcano eruption. This is volcanic. Volcanic is any moving rock. We've got moving rock, molten rock underneath the earth. We have molten rock hitting the surface, hitting the water and freezing. When we actually look at this ocean floor, we see basically three bands. We see basalt at the top. This is all mafic rock, about 3.0 grams per cubic centimeter, which differentiates between the continental rock, which is about 2.7. This makes up basalt, makes up gabbro, the extrusive and intrusive form, where we get rhyolite or granite when we talk about continental rock. This tends to be a little bit more dense, and if we take a look at it, we see a basalt layer on the top. We get columbar or columns of basalt, which shows slower cooling underneath, and the very bottom row of this is a gabbro, which is the intrusive form, phaneritic, large crystal, intrusive form of mafic rock. But anyway, what we get is asthenospheric convection, which actually moves up towards the top and breaks away to the left, breaks away to the right, and actually pulls these two plates apart. There may be something called slab pull also on the other end, which is pulling it away, but this is probably a push force. It's probably a little bit of both. So this moves over, and what it does, it rips the oceanic crust away. New molten rock forms up to the top. The top part freezes very quickly, extrusive basalt. Bottom part very slowly, intrusive gabbro. And then the part in between is the medium. That's the columbar basalt, the columns of basalt. Okay, so what I'm going to do is I'm going to press play, and what we're going to notice is that these earthquakes are all going to be shallow, and they're all going to be sitting right next to each other along this line. They're all going to be shallow depth because this is molten rock. You can't build up the stresses. This is solid rock. You can. So the earthquakes all tend to be rather shallow, right up near the surface of the earth. One way we can tell this is a divergent force, and one way we can tell oceanic crust is thinner than continental. Okay, so that is the divergent boundary. We tend to make oceans with this. If there were like a continent here that started getting pulled apart, what we would get is we'd get mafic material forming inside. Eventually it would reach up and hit an ocean or a lake. It would fill full of water, and we'd have an inland sea and keep getting larger and larger, like what we think we happened at to form the Atlantic some 250 million years ago. Then we can go to convergent. Convergent means to come together. You can see we have arrows moving the opposite direction, just like we did here. These two arrows are moving opposite direction, opposite of each other. These are moving in opposite direction toward each other. And then transform, they're moving opposite directions side by side. So it all has to do with plate motions. They're all moving opposite direction. These tend to move closer. Two cars colliding, this tends to be a very violent earthquake. We are going to get shallow earthquakes right along this. This would be called a deep ocean trench rather than a spreading center. Rift Valley, where we had the divergent, this one is actually called a deep ocean trench or an ocean trench. These tend to be the deepest places in the ocean. So even shallow earthquakes located here are farther away from surface than shallow earthquakes or maybe even intermediate earthquakes on dry land. We also get a plate that is forced down, subducted down. It reaches into the mantle. the mantle's heat actually starts melting it. We get blobs of molten rock, which really want to be up here at the surface. They start being buoyant and they start moving up. Some of them will actually solidify in the crust. Some will make them way all the way up to the surface and create volcanoes. They're actually called seamounts before they hit the surface. But once they hit the surface, we actually call them volcanic islands. Now what's going to happen is this volcanic island is eventually going to get pushed into this trench and probably rubbed up against this other plate. But what you'll also notice is we'll get intermediate earthquakes, and we'll even get deep earthquakes with this one. But they seem to be lined up. The shallow earthquakes are here. The intermediate earthquakes, which happen down here, will appear as epicenters up here on the surface, and the deep earthquakes, which appear down here, will actually appear this direction. So we get deep, intermediate, and shallow earthquakes, all with this three-dimensional view. We still get earthquakes looking the same. We get volcanoes with the volcanic eruption looking the same. But this is a convective force pushing this plate into this plate, subducting one of the plate, probably the older and more dense of the oceanic plates, takes the dive. The other one gets rubbed away, and that material gets moved down as well, just probably not as fast as this side. So let me push play. You can see the two plates moving toward each other. They're not really moving the volcanoes. It would get rubbed in, and eventually they'd work their way in, but this is the one that gets subducted down. Let me show you the earthquakes while we're there. We do get deep earthquakes, intermediate earthquakes, and shallow earthquakes. But shallow, epicentral, would show the intermediate ones here and the deep ones over there. Last one is called a transform fault. It's caused by shearing forces. This one is actually caused by divergent forces being pulled apart. This one, convergent forces being pushed together. This one, transform faults, or shearing, moving back and forth, side to side. Notice that these two plates don't really move toward each other, so we're not getting one subducted down. They don't move away from each other. We're not getting molten rock rising to the surface. We get lots of earthquakes with this plate, but we get very little volcanic activity. Okay, we can get shallow, intermediate, and deep earthquakes depending on the depth of the crust, but they appear to be right over the top of each other, or at least very closely associated. Where divergent, they're all shallow in a line, and convergent, we get shallow earthquakes where the two plates are touching. We get intermediate earthquakes and deep earthquakes depending on which plate is being subducted down. Okay, this one can be found in the water, can also be found on dry land. They're showing this one on dry land because they're not really showing you water as they did in the other ones. But basically what we get is we get lots of earthquakes with no volcanism with this type of boundary. Let me push play, and you can see this one moving. You can see shallow earthquakes. There should be intermediate and deep earthquakes if the crust is deeper. This is what's called a lateral fault. This is a left lateral fault because the material on the other side of the fault moved to your left. Just like if you're standing on this side, that other side moved to the left. The San Andreas fault would be the exact opposite. It's a right lateral fault. But we have a lithospheric plate sitting on top of a asthenosphere. The asthenosphere is moving, or the plate's moving, and we get this side-to-side motion, transform, or shearing forces. Okay, and the whole thing plays out in something called plate tectonics, where we get out in the ocean, we get a divergent force with shallow earthquakes. We get convergent forces. In this one we're actually getting continental oceanic convergence rather than oceanic convergence. This was oceanic. This one is oceanic continental convergence. The continental plate being a little more lighter, less dense, 2.7 grams, is more buoyant, stays on the top. The ocean floor being more dense, made out of mafic material, 3.0 grams per cubic centimeter. Not a big difference, but difference nevertheless. It's about a 10% difference. So this one is the one that takes the dive. It actually does take sediment that's been washed off this and accumulated in this deep ocean trench. It takes some of that continental material down with it. Most of it is mafic. It does melt just like it did before. This plate will eventually be destroyed completely. But we do get molten rock rising up. Some of this molten rock is buoyant, and it actually moves up. Some not as hot and actually solidifies. The mafic material usually ends up down below, and it gets more felsic as we go up, so we can get andesitic volcanoes. Andesitic meaning you get a little bit of mafic and you get a little bit of felsic, and this one actually is probably some of the strongest, most violent earthquakes. Mount St. Helens, Mount Rainier, Mount Mazimov, which is Crater Lake, the Three Sisters, Mount Shasta, Mount Hood. All those volcanoes on the west coast of the United States are created by this convection force, where we have the Juan de Fuca plate being pushed into the North American plate, taking this dive and forming this whole pressure. Okay, stenospheric convection, pushing the plates apart, divergent, pushing one plate into another because we're on a round surface, and anytime I move something away from here and here, they got to be moving towards something else on both sides. So we get convective forces there. Transform forces are actually caused when we get divergent to this point, divergent to that point. At this one, that's actually moving to the right. This side's moving to the left, so they're actually moving side to side from each other. These really not faulting because they're moving pretty much at the same direction. This is a period over 100,000 years. Let's push play, and you can see divergent shallow earthquakes. You can see convergent with shallow, intermediate, and deep earthquakes. You can see volcanism coming out here. You can see volcanism coming out here. This one tends to be more mafic, more gentle eruptions. This one tends to be more intermediate, where we get mafic and felsic, the most dangerous type, composite cones. And this one, again, where we get the plates rubbing next to each other, no volcanism whatsoever. Shallow earthquakes. On this particular case, shallow earthquakes, but if it's the San Andreas Fault, we get shallow, intermediate, and deep. And here we get shallow, intermediate, and deep, where we actually get them shallow being in some place different than the intermediate, someplace different than the deep. For this one, we'd actually get them right on the top of each other. And this one, it's only shallow because of the thickness of the crust. Older as we move this way, and then subducted down. Older as we move this way, and eventually it'll reach either a continent, and it's the end of the floor, so you can see rock increasing age this way, rocks increasing age this way. If you looked 100 miles on this side and 100 miles on this side, the rock on both sides would be very similar to age, a lot older than what would be found closer to this mid-ocean ridge or this rift valley, this place of divergence, and eventually hits the convergence. If it hits an oceanic convergence, we get what's called an island arc. This would be called a volcanic arc, a line of volcanoes, arc-shaped. And that should do it. Thank you very much.